Good morning. Today's topic is magnetization. Before starting this topic, magnetization, I have to discuss a very important question that from where the magnetic property of magnet comes. The answer is that it starts from atom or the nucleus. As we know, all the electrons revolve in the nucleus around the nucleus in some permissible orbits. Electrons are negatively charged. So when this electron revolves around the nucleus, it constitutes a current loop, and every current loop behaves like a magnet. Or we can say every atom behaves like a tiny or a small magnet. It's represented like that. Suppose this is the atomic magnet. If the atomic magnet of a particular region are arranged in a same fashion or in a single direction, then this region has a net magnetic effect, and this region is called domain. Like that, if they are the magnetic substance, magnetic atomic magnets, this region is called domain. If all the domains of the substance, or let's say iron, are arranged in a single direction, then this substance, or we can say iron, behaves like a magnet. Otherwise, we have no property of iron. The common difference between the two is, suppose this is iron and domains are randomly distributed in different directions. It means all the domains cancel or neutralize each other's effect. There is no net magnetic effect. But if we apply external magnetic field, the external magnetic field exerts the torque on these domains or magnets. So these domains align in the single direction, in the direction of the applied magnetic field, and the situation is like that. Now the torque acts on the dipole or the small domains. The magnets or all the domains align in a single direction or in the direction of external magnetic field, and this iron behaves like a magnet. This is the only difference between iron and magnet. In case of iron, all the domains are randomly distributed, net magnetic effect is 0. But in case of magnet, all the domains are aligned in the same direction or single direction in a common fashion. They reinforce each other's effect and they have net magnetic effect. This is called magnet. So this process is called magnetization. Now suppose if we heat or beat the magnet, then the alignment of the domains get disturbed and it becomes a iron. This is called demagnetization. This is all about the domain theory of iron, or we can say a ferromagnetic substance. Now I come to the topic magnetization. Magnetization means when a magnetic substance placed in an external magnetic field, it behaves like a magnet. Suppose this is a magnetic substance and we applied external magnetic field, say B0. This becomes a magnet. This is called magnetization. Now we have to discuss some important terms in the magnetization. Very first is magnetizing field intensity. Magnetizing field intensity, represented by H. The external magnetic field used in the process of magnetization is called intense magnetizing field intensity, represented by H. Number 2, magnetic induction. Magnetic induction, represented by B. This is a magnetic substance, iron. We applied a magnetic field, say B0, And due to magnetization, some magnetic field also induced inside this substance. So the total magnetic field inside this substance iron is called magnetic induction. Number 3, magnetic permeability. Magnetic permeability. As you know, magnetic permeability is the property of the substance or the medium, we can say iron, and it is defined as the ratio of magnetic induction to magnetizing field. So, magnetic permeability of the medium or the iron is defined as the ratio of magnetic induction to magnetizing field. B is equal to B by H. Next is relative magnetic permeability. As you know, the relative density is obtained by dividing the density of substance by density of water. In the very same way, the relative magnetic permeability is obtained by dividing the permeability of the substance by the permeability of space. Or we can say mu r is equal to mu upon mu naught, where mu is the magnetic permeability of this material. Now next, point is intensity of magnetization. Intensity of magnetization. Intensity of magnetization indicates that to what extent our magnetic substance get magnetized. Suppose due to magnetization, the magnetic dipole moment induced is M. Then magnetic dipole moment induced per unit volume of the substance is called intensity of magnetization, represented by capital M is equal to small m upon V. This is the intensity of magnetization. I is equal to m upon V. Next point in this discussion is magnetic susceptibility. Magnetic susceptibility. It is also the property of the material, we can say the iron in this process. It is defined as the ratio of intensity of magnetization upon magnetizing field H. Magnetic susceptibility is the ratio of magnetizing intensity of magnetization upon magnetizing field intensity H. Now, the next point, I have to derive a relation between permeability and susceptibility. Suppose there is a magnetic substance of magnetic permeability mu and magnetic permeability, relative magnetic permeability mu r. So mu r is equal to mu upon mu naught. Is placed in an external magnetic field of magnetizing field intensity H. Then the total magnetic field, we can say the magnetic induction B is equal to mu naught n plus H. This is total magnetic field inside the magnetic substance, or you can say magnetic induction. But B is equal to mu H. Now by putting the value B in the equation, we can say 1. What we get? Mu H is equal to mu naught H plus N. Now dividing both the sides by mu naught H. Mu naught H. what we get, mu over mu naught is equal to 1 plus m upon h. And now mu naught upon mu is equal to the mu r, and m upon h is susceptibility. So we can write mu r is equal to 1 plus chi. This is the relation between permeability and susceptibility. Here we get that m because it is the magnetic susceptibility. Now, as you observe, when a piece of iron brings near a magnet, it also becomes a magnet. Just like when we bring a nail, or we can say screwdriver, near a magnet, then the screwdriver has the ability to attract small screws and pins. Why it is so? Because the screwdriver becomes a magnet, and it attracts the screwdrivers. Now, topic is hysteresis. Next topic is hysteresis. Suppose there is a magnet and we bring a nail near it. We can say near an iron, we can say screwdriver. If magnet has a magnetic field, say B naught or magnetizing intensity H, and this nail screwdriver attain a property of magnetization or a magnet. If we take this screwdriver away from this, it again retains some property of magnet. This is called hysteresis. Hysteresis means lagging of magnetic induction behind magnetizing field intensity is called hysteresis. So what is hysteresis? When magnetic induction lags behind the magnetizing field. This is called hysteresis. Hysteresis. It can be explained by using a graph with the x-axis, with the y-axis. Take magnetizing field intensity H here, magnetic induction on y-axis B. As we increase H, or you can say the magnetizing field, the B also increases, becomes a maximum or becomes saturation. As we decrease the magnetizing field, the B also decreases, but when H becomes 0, B doesn't become 0. If we increase H, or we can increase H in opposite direction, decrease H, or we can say increase H in negative direction, magnetic induction decreases like that and becomes 0 at this point. We again increase H in opposite direction, and by completing we get a loop like that. By increasing H, the behavior is B like that. This magnetic induction remains inside the magnetic substance. When magnetizing field becomes 0, is called retentivity. Retentivity means magnetic induction remains in the magnetic substance. When magnetizing field becomes 0, is called retentivity. This H is called coercivity. Means the magnetizing field in opposite direction for which the magnetic induction becomes 0 is called coercivity. So, this is called hysteresis 2 or hysteresis curve. Hysteresis curve. When we increase H, it means we have to magnetize the substance. When you decrease H, it is the demagnetization. So in magnetization and demagnetization, loss of energy takes place. The loss of energy in this process is called hysteresis loss. The area of this loop, or we can say the hysteresis curve, represents the hysteresis loss. As the area increases, the hysteresis loss also increases. Now, an important question here: okay, why does temporary magnets are made of soft iron and permanent magnets are made of steel or aluminium? Now, here we have to draw hysteresis curve for two substances. First, say for iron, this is hysteresis curve for iron, and this is the hysteresis curve for steel or aluminium. This is for steel or aluminium. Aluminium, this is an alloy, aluminium, nickel and cobalt. What we observe here, that in case of iron, the retentivity is comparatively, in case of iron, retentivity is higher, but coercivity is small. But in case of steel, coercivity is high as well as retentivity is also high. It means magnetization and demagnetization of iron is easy, but magnetization and demagnetization of steel or aluminium is very hard. So permanent magnets are made of steel. It means once they hold a magnet, it is very difficult to demagnetize it because its coercivity is very high. And when you have to make temporary magnet, we use iron because its magnetization and demagnetizations are easy.